Click the bell icon to get latest videos from Ekeeda.
Hello friends, today we will discuss about the concept, construction and working of unijunction transistor. So unijunction transistor, which we termed it as a UJT. Now in UJT, it is called as a unijunction. Uni means single junction, that is in this transistor, it is having only one PN junction. Since it is having only one PN junction, this transistor is named as a unijunction transistor. But it is different from the ordinary diode, because in ordinary diode, PN junction diode, it is having only two terminals, but in case of unijunction transistor, it is having three terminals. So unijunction transistor is a three-terminal device. The name of the terminals are emitter, base 1 and base 2. Unijunction transistor is separate, or it is different in working when we compare with a bipolar junction transistor or field effect transistor or MOSFET. So UJT, it is only a single PN junction, but it is not a diode, it is transistor, because it has three terminals, that is emitter, base 1 and base 2, but it is different than the transistors BJT, FET or MOSFET. Then we will discuss about the construction of this unijunction transistor. The unijunction transistor construction, it consists of N-type semiconductor bar, which is made up of silicon, and it consists of P-type semiconductor bar. Now from this N-type material, two terminals are taken out, and from P-type material, one terminal is taken out. This N-type material is usually lightly doped and this P-type material is heavily doped. Means the number of charge carriers are less in N-type and number of charge carriers are more in case of P-type material. This region of N-type is called as a base region, and this region of P-type is called as a emitter region. As the number of charge carriers are less in N-type, it is having lightly doping, so the resistivity is very high in case of N-type. In case of P-type, since it is heavily doped, the number of charge carriers are large, so the resistivity is less. So we can say that for N-type, that is base region, resistivity is very high. In case of P-type material, which is emitter region, charge carriers are more, so the resistivity is less. Now from base region, two terminals are taken out, that is base 1 and base 2. And from emitter region, one terminal is taken out, that is emitter. So these are the three terminals of UJT: emitter, which is taken from the P-type material, and from base, that is n-type material, two terminals are taken out, which is termed as base 1 and base 2. So it can be abbreviated as B1, B2 and E. The next is, as we have seen the construction of the UJT, the next is equivalent circuit. As UJT contains n-type material and p-type material, so there is a formation of p-n junction, and p-n junction can be represented as a diode. So this diode represents the p-n junction, and these are the internal resistance of the base region. So here the terminal is B1, terminal is B2 and the terminal is emitter. So this diode represents the PN junction in UJT, and this RB1 and RB2 are the internal resistance of the base region. So it is called as a interbase resistor. So we can write down that interbase resistance as RBB is equal to addition of both the resistors. As the resistor RB1 here is shown as a variable resistor, its value will vary if we apply the voltage. The value of RB1 is shown as a variable because when the supply is given between the emitter and base 1, the value of the resistance RB1 will change, and because of that it is represented as a variable resistor. So its value can be vary from 4 kilo ohm to 40 ohms. The minimum value, when the conductivity is very high, the minimum value across the RB1 is 40 ohms, and maximum value when there is no supply voltage, the maximum value obtained across this RB1 is a 4 kilo ohm. So it is having three terminals, emitter, base 2, base 1, which is the equivalent circuit of UJT can be represented as, it consists of diode which represents PN junction, RB1 and RB2 represents the interbase resistors or internal resistors of the base region. Then next we will find out the intrinsic standoff ratio. So here we are using the PN junction diode which represents the PN junction at UJT. This terminal is emitter. Then there are two interbase resistance, RB1 and RB2. This terminal is base 2. This terminal is base 2. This terminal is base 1. And we connect the supply voltage externally across both the base resistors. And we term the supply voltage as a VBB. So here is the resistor which is RB2 and here is the resistor that is RB1. As when we apply the voltage VBB across RB1 and RB2, we will find out the voltage drop across RB1, which we termed it as a V1. So voltage drop across RB1, that is V1, is equal to the resistor across which we are finding the voltage drop, that is RB1, divided by total resistance into supplied voltage, which is nothing but VBB. This is the interbase resistance, which we can write it as RB1 divided by RBB into supplied voltage VBB. So V1 is equal to, this can be represented as eta into VBB. So RB1 divided by RBB is called as intrinsic standoff ratio, which is represented as eta. The value of eta is usually lies between 0.5 to 0.8. So this is the voltage drop across the resistor RB1, which is nothing but eta times VBB. And this voltage is given to the cathode terminal of the diode. So this is intrinsic standoff ratio, which is nothing but eta, and it is equal to RB1 divided by RBB. Next, we will discuss about the UJT operation, that how the UJT operates. PN junction diode. This is the emitter terminal. These are the internal resistors of UJT between base 2 and base 1. This resistor is RB2, this resistor is RB1, and now we will provide the supply voltage to the base region as well as emitter region. So we connect one power supply between the two base terminal, that is base 2 and base 1, and that supply voltage is VBB. And we provide the supply voltage between emitter and base 1, that is equal to VEE. This is the supply voltage which is given between the emitter and base 1, and VBB is the supply voltage given to the base 2 and base 1. Now, because of VBB supply voltage, the voltage drop across RB1 is always eta times VBB, and that voltage is applied to the diode. So when the input voltage, that is VEE, is very less, at that time the voltage at the cathode is eta times VBB plus the voltage drop across the diode. So the voltage at the cathode is eta times VBB. Now the value of supply voltage must be increased beyond this value, then only this diode will be on. So the voltage at which the device is on or the diode is forward biased, that is called as a peak point voltage. The voltage across RB1 is eta times VBB, which is applied to the cathode terminal. So the input voltage must be greater than this value by eta times VBB plus VD, then only the device will be on, or it is said as UJT is fired or it is triggered. So VP is the peak voltage which is equal to VD, that is the diode drop, which is nothing but 0.7 plus eta times VBB, which is the voltage across the cathode plate. So when this much voltage is given to the UJT, to the emitter terminal, then only this diode will be forward biased and the current IE will start flowing through the emitter terminal. So as you increase the supply voltage, the emitter current goes on increasing. And as the emitter current increases, the maximum holes will move from the p-type region to the n-type region. And as the maximum holes are moving from p-type to n-type, the resistivity of the base region, that is base 1, goes on decreasing. So this value eta VBB also goes on decreasing as the input current increases. So we can say that when the value of VEE, that is supply voltage, increases beyond eta VBB plus VD, then the emitter current will start. This voltage is peak point voltage. At peak point voltage, the current is IE, and as VEE increases, the value of IE also increases. But at the same time, when the holes will move from P type to N type, the conductivity increases and the resistivity of this base region decreases. So this is called as a conductivity modulation. As the conductivity of the base region increases, the value of RB1 goes on decreasing. So this is about the UJT operation, which is having three terminals, emitter, base 2 and base 1. We have connected one supply across the base 1 and base 2, second supply across the emitter and base 1. The voltage drop across the RB1 is eta times VBB, which is applied to the cathode. So the voltage applied to the diode must be eta times VBB plus VD, then only the diode will be on or forward biased, and when it is forward biased, it is said that UJT is triggered or UJT is fired. Then when current IE increases, maximum holes will move from P region to the N region, and as they move from P region to N region, the resistivity of the base region, which is nothing but N type material, so the resistivity of this region decreases and the conductivity increases. So this increase in conductivity is called as a conductivity modulation. Then the next is VI characteristics of UJT. So it is the graph of V versus I. This graph is basically divided into three regions. The region which is to the left side of peak point is called as cutoff region. Then the region in which the value of the voltage decreases is called as negative resistance region, and the region beyond this is called as a saturation region. So this VI characteristic is divided into cutoff region, negative resistance region and saturation region. Now in cutoff region, the UJT is off because the voltage at the cathode terminal in case of diode is eta times VBB and supply voltage is less than that, and because of that the diode is reverse biased, and due to that the UJT is off. Then at this voltage, that is VP, which is peak point voltage, the UJT is on. So at VP the value of the voltage is equal to eta times VBB plus VD. So at this voltage the UJT will be on. Then as the current increases due to supply voltage, the maximum number of holes will move from the P region to N region, that is from emitter region to base region. Due to that the conductivity increases and resistivity decreases, and as the resistivity across the RB1 decreases, the voltage drop across the RB1 also decreases, and because of that there is a drop in the voltage from V peak to this voltage, where the voltage is minimum value is called as a valley voltage. So the region from V peak to V valley is called as a negative resistance region. Why it is negative resistance region? Because in this region the voltage decreases from V peak to VV, that is peak point voltage to valley voltage, but at the same time the current increases from I peak, that is peak current, to the valley current. So as one quantity increases and other quantity decreases, this is called as a negative resistance region. Then the next region is called as a saturation region. In saturation region, the value of emitter voltage remains approximately constant and current increases. Thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda.